Hi, welcome to the video introduction to Module 4. In this module, we will begin learning about hypothesis tests, and we'll do so using simulation-based methods that will allow us to focus on the concepts instead of doing lots and lots of calculations. Now, to begin with, a statistical test is a way of using data from a sample to assess a claim about what's happening in the larger population. And more formally, these are referred to as hypothesis tests. Now, the first thing that we'll need when we do hypothesis tests are some hypotheses that we can test. So statistical hypotheses, we'll use two of them. They're called the null hypothesis, which we give the notation H sub 0, and the alternative hypothesis, which we give the notation H sub A, and they're usually written in this order. Now, whenever we're writing hypotheses, it's because there's some claim that we're trying to decide if we have strong evidence in favor of. And that claim that we're trying to support, and which we seek evidence in favor of, is always going to go in our alternative hypothesis. So sometimes it's easier to figure out what that one is first, even though we always write it second. And the null hypothesis is going to be that the alternative is not true, that often this is that there's no effect or no difference from what is expected or established. And our convention in this course is that the null hypothesis will always use an equal sign when we're writing the null hypothesis. So keep an eye out for that in the textbook and some extra examples. As a note, hypotheses are always about population parameters like the population mean, mu, or the population proportion, p. They are never written about statistics like x bar, the sample mean, or p hat, the sample proportion. Now, the reason for this is that once we collect the data, we will know exactly what the values of the sample statistics are. So we don't need to make hypotheses about those. What we don't know the value of is what's happening in the entire population, our population parameter. So make sure when you're writing hypotheses that they're always about the parameter, never about the statistic. Quick example, looking at penny spinning. My friend told me recently that if I spin a penny on its edge until it falls over, that it's more likely to land tail side up than head side up. Now, I'm not going to believe my friend unless I have strong evidence that heads and tails are not equally likely to occur. So what are my hypotheses? My hypotheses need to be about the population parameter, and the one that I'm interested in here is going to be P, the proportion of all penny spins that land tail side up. I know I'm interested in a single proportion P because I have one categorical variable for each of the penny spins that I'm going to do, and I'm going to do 50. I am going to record whether the penny lands tails or heads facing up. So since one categorical variable, one proportion P is my parameter of interest. Now, I'm trying to see if I've got strong evidence that pennies are more likely to land tail side up. So that's going to be my alternative hypothesis. Tails is more likely, which would mean that the proportion that land tails up has to be more than 0.5, more than half. My null hypothesis then is going to be that the alternative is not true and that heads and tails are equally likely to occur. P is equal to 0.5. So there are my hypotheses. Now the key idea is I am going to take a sample of 50 penny spins and I'm going to decide, does the sample give strong evidence that the null hypothesis is not true, that it's not a 50% chance of getting my spinning penny land tails up? If so, then we'll reject the null hypothesis and conclude that there's convincing evidence that the alternative isn't true. So what I'm always focusing on when I'm doing hypothesis testing is I'm always deciding whether the sample is consistent with the null hypothesis or not. If it is, then I won't reject it. If it's not, then I will. Now, in order to decide if my sample is consistent with the null hypothesis, I need to know what kind of sample statistics might occur by chance if the null hypothesis is true. And this is what's called the randomization distribution. It's a distribution of sample statistics that are generated under the assumption that the null hypothesis is true. By having a randomization distribution, it's going to allow us to decide if our sample is consistent with the null hypothesis. So here's an example of a randomization distribution. If the null hypothesis is true, what proportion of my 50 spins do I expect will land with tails facing up? Well, if I just think about it, I say, well, it should be about half, so about 50%. But I know that that will vary from sample to sample. It's not always going to be exactly 50%. So this distribution of results here, simulated assuming that p is equal to 0.5, and with a sample size of 50, shows me how the sample proportions, p hat, might vary from sample to sample. If I see a sample proportion of something like, say, 0.55, something around here, I'll say, wow, that's something that is, not that unlikely to have happened by chance. That would be consistent with the null hypothesis. On the other hand, if I saw something way out here, I'd say, wow, there's very little chance that I would have seen a sample proportion of 0.74 or more if really there's a 50% chance of each coin landing tails up. So that would give me strong evidence against the null hypothesis. So the idea is going to be that these values that are far out in the tails of our randomization distribution are going to give us strong evidence against the null hypothesis, and values that are not so far out are going to give us not very strong evidence that won't lead us to reject the null hypothesis. So this brings us to the idea of statistical significance, which is probably something you've heard discussed before, but may not know exactly what it means. So when results as extreme as the observed sample statistic are unlikely to occur by random chance alone, assuming the null hypothesis is true, then we say that the results are statistically significant. If our sample is statistically significant, we have convincing evidence against the null hypothesis and in favor of the alternative. If our sample is not statistically significant, it does not necessarily mean that the null hypothesis is true. What it means is that our evidence is not so strong that we're ready to reject it, and we say that our test is inconclusive in that situation. So what we're going to need is a way of measuring how likely or unlikely to occur by chance our sample statistic would be. And we're going to measure this with something called the p-value. The p-value is the probability of obtaining a sample statistic as extreme as the observed sample statistic, or even more extreme, assuming that the null hypothesis is true. A small p-value means the sample is not consistent with the null hypothesis, and it will lead us to reject the null hypothesis. A large p-value means that the sample is consistent with the possibility that the null hypothesis might be true, and we will fail to reject the null hypothesis. So let's take a look at the data that I collected from my sample of 50 penny spins. In 32 of my 50 penny spins, the coin landed tail side up, which gives me a sample proportion p hat of 0.64. And I want to know, is this result something that I would reasonably expect to see by chance if p is equal to 0.5? To decide, I'm going to come to StatKey and I'm going to simulate the randomization distribution. Now, I did this before and I had a picture of it, but I want to show you how I would actually generate that randomization distribution. So from the StatKey menu, I'm going to go to randomization hypothesis test, and since my test is about a single proportion as my parameter, I'm going to click here. Now I'm going to edit the data to enter my own sample data. I saw 32 land tails up out of a total of 50. And that gives me my sample proportion of 0.64 that I found earlier. Now what I'm going to do is I'm going to generate 1,000 samples and look at the proportion of times that I see something as extreme as my sample statistic or more extreme. So here we go. We've got 1,000 samples, and I want to know what proportion of the time I saw something as extreme as my sample statistic, 0.64, or more extreme. To find out, since I'm looking at my 0.64 and more extreme would be to the right, so I'm going to click on right tail. And I'm going to put this value on the bottom at my cutoff. Now it's there, but it's kind of in the middle of this. See how some of the dots are red and some are black? I'm going to click here and change it to 0.64, so it'll include all the values that are as extreme as mine or more extreme. And so my p-value here is 0.035. So there's my p-value. So the chance of seeing a sample statistic as large as 64%, 0.64, or even larger, if in fact there's only a 50% chance that each coin spun will land tail side up, is 0.035. That's pretty unlikely. So what is the probability of observing my sample statistic, a p-hat of 0.64, if p is actually equal to 0.5? That's our p-value, and we can find it here. It's 0.035. So should we reject the null hypothesis? When the p-value is small enough, we reject the null hypothesis. But how small is small enough? Before we do a hypothesis test, we really have to decide how small the p-value will need to be to reject the null hypothesis. And this is called the significance level of the test, and we give it the notation alpha. Usually we use alpha is equal to 0.05 or 5% for a significance level. This is convention. It's something that is generally regarded as the threshold for statistical significance for most journals and things like that in which people publish scientific results. When the p-value is less than alpha, we will reject the null hypothesis and say that our result is statistically significant. So back to our example. In our example, we had a p-value of 0.035. If we use a 5% level of significance, our p-value is less than 5%, so we reject the null hypothesis. Remember, our null hypothesis was that heads and tails are equally likely. We've rejected that null hypothesis and have strong evidence in favor of the alternative, that tails is more likely. So we can conclude that there is strong evidence that when spinning a penny, it is more likely that the penny will land tail side up. I hope this video introduction is helpful as you get started in Module 4. As you do, make sure that you read carefully all of the sections 4.1, 4.2, and 4.3. It's probably also going to be helpful to you to watch the video tutorials on each of the learning goals in those sections. I'm sure that most of you will have some questions as you get started working through the module and doing the homework. As questions come up, don't hesitate to let me know. You can post questions to the help discussion board. You can also let me know if you'd like to have an office hour. I can do them either online or I could do them in my office for people who are in the Burlington area. So I'm happy to help and I look forward to getting your questions. Have a good day.